All right, welcome back everyone to the Fractional Calculus online seminar series. Today we have a presentation from Professor Erkinjon Karimov. He is a researcher specializing in partial differential equations of integer and fractional order and special functions connected with such PDEs. He is affiliated with Ghent University, where he conducts research on direct and inverse problems for PDEs. Dr. Karimov has published more than 50 papers contributing to advancements in direct and inverse problems for fractional order PDEs and mixed type PDEs. Dr. Karimov holds a PhD from 2006 and DSc from 2020 from VI Romanovsky Institute of Mathematics, Uzbekistan Academy of Sciences, where he focused on direct and inverse problems for PDEs of various types, including mixed type. Throughout his career, he has collaborated with researchers from the University of Santiago de Compostela, University of Las Palmas de Gran Canaria, Sultan Qaboos University, etc. His projects have been supported by the State Agency for Science and Technology of the Republic of Uzbekistan, ICMS, Great Britain, ICTP, Italy, TWAS-CAS, China. In addition to his research, Dr. Karimov is actively involved in teaching, mentoring, and managing scientific journals. And today he is going to speak to us about multivariate Mittag-Leffler-type functions associated with the Prabhakar Fractional Calculus. Please go ahead, the floor is yours.
Thank you very much, Arran. It's my honor to give a talk in this seminar. Let me start my talk with the content. Probably I need to I cannot move the slide.
Yes, we can only see the first slide still, the title slide.
Still the title slide. Now is okay, yeah?
Yes, yes.
Okay, I will start my talk with the general single variable special functions of the fractional calculus, namely H function and the Fox-Wright function, and also the Leroy-type generalization of these functions, I function of Reti and the bar H function, etc. And then I will slightly move to the multivariable special functions of fractional calculus, mentioning the functions introduced by Gorenflot-Luchko, Saxena-Kalla, and also I will talk about bivariate Mittag-Leffler-type function and also trivariate Mittag-Leffler-type function. Then a short introduction to Prabhakar Fractional Calculus will be presented, and then applications. I will move to the applications. First, I will mention some works on Cauchy problems for differential equations involving the various type Prabhakar derivatives, and then move to our results regarding the bivariate and trivariate Mittag-Leffler functions, including applications in fractional PDEs. We will consider the Gursa problem and then the local inverse problems as well. So let me talk about the Fox H function. In 2021, it was published Virginia Kiryakova's survey paper, where she mentioned two most general special functions, which are related with the fractional calculus. First one is Fox H function, which is presented by formula 1. And another one is a Fox-Wright function, which is given by the formula 2. We need to note that this Fox-Wright function can be represented by H function as well. So there is another survey paper by Kiryakova and Paneva-Kanovska, where they highlighted the importance of more general functions, Leroy-type generalization of Fox H function and Fox-Wright function, also I function introduced by Ratti. This is a I function of Ratti. You can see that it's more general than the Fox H function. And also they call bar H function, or generalized Fox-Wright function. This generalization related with Leroy-type generalization. So you can see here power of gamma functions. So as you see, bar Fox-Wright function also can be written via the bar H function. So these general special functions of a fractional calculus of single variable can generalize a series of Mittag-Leffler-type function of single variable, and most of properties studied for these functions can be directly applied for other functions as a particular case. But I have to note that in a particular case, more properties can be proved rather than in general case. So that is why the special cases also interesting to study, to use. So now let me move to the multivariable Mittag-Leffler functions, which are main subject of this talk. There is a multivariate generalization of a classical Mittag-Leffler function, which is given by formula 6. It was introduced by Gorenflot and Luchko, and the official publication appears in 1997 by, I believe that the preprint was ready in 1995. So this function was introduced and studied, motivated by boundary value problem for linear fractional differential equations with a constant coefficients. This function appears in the solution. So the several scientists studied their properties of this function, namely recurrence formulas, differentiation and integration formulas, some asymptotics. So I can mention work by Yamamoto and others. There is also the generalization of this multivariate function, which was introduced by Bajlekov and Bajlekova in 2021. It is called like a multinomial Prabhakar function. So you can see here the generalization with this. So for this function also certain properties were studied: recurrence relation, integration and differentiation formulas, and also the complete monotonicity as well. This is also important, and asymptotics as well. So I need to mention also another multivariate function introduced by Saxena and Kalla. So you can see by in the formula 8. So as a particular case, it will contain this previous function as well. For this function as well, recurrence relations, differentiation, integration formulas, moreover, these integral operators for the kernel containing this function were studied. And this function was introduced in 2011 by Saxena and Kalla. So as you see, these multivariate functions also have own applications. So Gorenflot-Luchko function appears in the multi-term fractional differential equations in the solution. So there was another bivariate Mittag-Leffler-type function, which was introduced in 2013 by Garg, Manohar, Kalla. And this function, you see that the generalization appears here. When alpha 1 is equal to 1, beta 1 is equal to 1, you can get the particular bivariate case of Saxena-Kalla function. Delta 2, alpha 3, delta 3, beta 3 should be also equal to 1. But this is also was interesting to introduce and study certain properties, and this function also can be used as in the solution of fractional differential equations. We used this function in our work with colleagues from Sultan Qaboos University when we consider non-local boundary problem. So this function also can be used as a solution because it generalizes classical Mittag-Leffler functions as well the Prabhakar function and the other single variable functions. So at that paper, they introduced another bivariate Mittag-Leffler function, which is more general. So you can see here beta 1n appears. So this is if you write the Bohamber symbol as a ratio of two gamma functions, the one gamma function will appear in the numerator, the combination of two parameters of infinite series. So this function was introduced but not studied, and we faced this function when we started to study the Prabhakar differential equations. So the fractional differential equations involving the Prabhakar fractional derivative. So with Professor Hasanov, we proved the Euler-type integral representation and estimations, upper bound for this function, and also the integration and differentiation formulas. So we just write the solution of the Cauchy problem involving the regularized Prabhakar fractional derivative with this function. I will talk about the solution of this kind of Cauchy problems later on. Then we, with the Professor Hasanov, we introduced the series of bivariate Mittag-Leffler-type function based on Horn hypergeometric functions. As you see, this kind of multivariate, even the single variable Mittag-Leffler-type functions, the Fox-Wright function based on the general hypergeometric function FPQ. And so that is why we started to introduce the bivariate Mittag-Leffler function based on the Horn hypergeometric functions. So here, 5 these kind of bivariate functions were introduced, and also we continued other types of bivariate Mittag-Leffler functions, which were introduced by this Garg Kalla E1, E2. So we introduced in total 11 this kind of bivariate functions. So this D1 function was studied in detail in this preprint. Unfortunately, it's not published yet. It's still under review, more than 2 years. And then D2 was studied by Hasanov and Nemajanov in a recent publication. So I would like to note another kind of bivariate Mittag-Leffler type functions, which was introduced in 2019 in the work by Ozarslan and Kurt, and they introduced this kind of bivariate Mittag-Leffler type function. And also they studied very deep analysis of fractional related to the fractional calculus in the next paper as well, the Kurt, Ozarslan, Fernandez. So these 2 papers contain all these properties of this bivariate Mittag-Leffler function. In this work in 2021, the authors introduced in the next paper, they introduced the 2 unified family of bivariate Mittag-Leffler type functions. So you can see here in the numerator the Pochkamber symbol, which contains the combination of Mn, which are parameters of infinite series. So here, 2 separate ones. So, they studied in a systematic way, and also they considered all particular cases, mentioning these properties. Based on this approach, authors introduced trivariate Mittag-Leffler function. So here, 3 unified family. So you can see here the combination of Mn chi, and here M plus N Ck, Mn q separately. So 3 unified families. They also studied many properties of such functions, and also they considered application where they appear. So the first application is a couplet system of linear homogeneous constant coefficients fractional differential equations with a Caputo fractional derivative, where the fractional orders are between 0 and 1. So there is initial conditions as well, And they found a solution of this couplet system in an explicit form, representing it through the trivariate Mittag-Leffler functions introduced above. So this was just the application of this newly introduced the trivariate Mittag-Leffler functions. So later on, the Professor Hasanov and Yuldasheva, it is the recent publication. So they introduced another kind of trivariate Mittag-Leffler-type function based on Laurent-Cheller's hypergeometric functions of 3 variables. So this is the first trivariate Mittag-Leffler function. You can see here more general forms. So there is another one, FB. So you can see the differences, FC, and also the FD. So they introduced 4 trivariate Mittag-Leffler type functions, and they studied the convergence regions, corresponding system of hypergeometric partial differential equations, Euler-type integral representations, Laplace transforms, the Riemann-Leibel derivative integral applied to these trivariate Mittag-Leffler functions. Now let me go to the basic elements of Prabhakar fractional calculus. So the first is Prabhakar function was introduced in 1971 in this paper, and this is just a generalization of Mittag-Leffler type function. So after Prabhakar introduced also the integral operator containing this Prabhakar function and solved this integral equation. So this is the operator applied, and so they found f of x in this form. So, but they didn't systematically study this inverse operator. But later on, in 2004, Kilbas, Saigo, and Saxena, they introduced the left inverse operator of the fractional integral, and they studied certain properties. But nowadays is more a popular one is a particular case of this left inverse operator. So here the fractional order of this Riemann-Leibel derivative is equal to m, so it is integer. So this version is most popular, and we call it Prabhakar derivative of Riemann-Leibel type. So Caputo type of this Prabhakar derivative was introduced by Ovidio Polito. The official publication appears in 2018, but the preprint was available in 2013. So we can count it, introduce it in 2013. So then in 2014, Gara, Gorenflo, Polito, and Tomowski introduced the Hilfert-Prabhakar fractional derivative. When the fractional order is between 0 and 1, they introduce it in this form. So this is just another notation of the Prabhakar fractional integral. And so this was just for the order between 0 and 1. But later on, in general form, this Hilfert-Prabhakar fractional derivative was introduced in this work by Arran, Fernandez, Nusha Rani, and Tomowski. So they studied many properties of this operator and also some applications. So I will mention some application which is given in this work. So here the Cauchy problem. So Cauchy problem, where in time variable, the Hilfert-Prabhakar fractional derivative was applied. So we get the fractional heat equation. So with the certain initial conditions related with the Hilfert-Prabhakar operator. So they found the solution in this infinite series of the Prabhakar function. So as I know, this was the first representation of the solution where the Prabhakar derivative was involved and as an infinite series of the Prabhakar function. So nowadays, there are ongoing research on the Cauchy problem for such equations. For example, Anwar Hassanov with his student considered the Cauchy problem for regularized Prabhakar equation. They used the Mellin transform to find the solution. Also, they're represented by E2. And then, as you see here, we got this infinite series of Prabhakar function, but how they prove the uniform convergence? They used the asymptotics of the ratio of gamma functions. So they, based on the approach which was introduced in 2011 by Saxena and his co-authors. And this kind of solution was obtained using Mikuchinsky operational method for the differential equations involving the regularized Prabhakar derivative. So you can find in this work, and the Hilfer-Prabhakar derivative in this work. So, and I will come back to this publication later on when we consider multi-term. So this paper contains also the multi-term case as well. So here, I would like to mention also these works by Professor Bulavatsky, which was published in 2017. And this equation was related with the applied problem. And here you can see the regularized Prabhakar derivative. And he also considered Hilfer-Prabhakar case as well. So this is the initial boundary problem. And also the solution was presented as an infinite series of Prabhakar function. So this paper is not so well known. I don't know. I was also aware a bit later on. So now new bivariate Mittag-Leffler-type function, which was connected with the Caputo-Prabhakar derivative, was introduced by Tarasov. So this work is published in 2022. So in general, this paper is related with an application in fractional dynamics related to the economical problems as well. So he introduces this kind of bivariate Mittag-Leffler type function, which can be represented as an infinite series of a Prabhakar function. So after just later on introduced single variable in this form. So the both variable x and y depends on t. In the previous lectures, Professor Bajlekova mentioned that in reality we deal with a single variable, so that's why we just name it as like a multinomial. So this is also some proof of this. So the author introduced this single variable and then represented the solution of this Cauchy problem with this single variable function. And he studied certain properties of this function as well. And regarding the asymptotics of this function, he just gives some details in a particular cases and also the application in economics. So let me come back to the bivariate function E2. So in this paper, we just used the solution which was obtained by Rani and Fernandez, which was given just an infinite series of Prabhakar function. We're just using this series form of this function. We just rewrite the solution. We didn't do any approach. We just got this solution as an infinite series of Prabhakar function, and we rewrite via the E2, and then used it in solving boundary value problems for the sub-diffusion equation involving the Prabhakar, regularized Prabhakar derivative. But later in this work, we solved the appropriate Cauchy problem with this regularized Prabhakar derivative reducing it to the integral equation and solving it by successive iteration method. So this is just another approach to get the same solution. So this solution was obtained using the Laplace transform, and then by Garra and co-authors, and then Mikuchinsky operational method by Arran, Fernandez and co-authors, and we just used the integral equation to get the same solution. So in order to use the properties of E2, we just got the integral representation, Euler-type integral representation, but with certain restriction on the parameters. We got this integral representation and then estimate for this function. So it is estimated by some constant depending on beta and gamma. So here the particular case which appears in the solution. So we didn't generalize these cases, just we wanted to get exactly the estimate of the particular case what we have in the solution. So later on in the mentioned work here, we found another integral representation which was represented by the product of right type functions. And also we got another kind of restriction to the parameters. And using this integral representation, we got another kind of estimate. And also here you can see the arguments which appears in the denominator. So it is not just estimated by the constants. So you can see the arguments as well. But unfortunately here the theta is very small. So between 0 and 1.5. So this kind of conditions appears because of the arguments of gamma functions. So that is why this estimate doesn't help us to reduce the regularity conditions imposed on the given functions. But still, we used this estimate. Now, using these results regarding the E2 functions, my PhD students got several results. So Hujakulov studied initial boundary value problem for sub-diffusion equation with the regularized Prabhakar derivative on graphs. So it was published in this journal in 23. And another my students investigated dynamic boundary conditions. So it is a bit non-local. Also here the diffusion wave equation, also the regularized Prabhakar derivative. So it is published in the same journal. So another my students considered the combination of a time fractional wave and a diffusion equation. Also here the regularized Prabhakar derivative is considered, but in space variable he considered the Bessel operator. So let me just show one of them. It's kind of mixed equation. So here we write in one like a compact form, but you can see here when t is less than a, so this derivative remains, but this one disappears. So you get the fractional wave because the fractional power is beta 1 is between 1 and 2. So fractional wave when omega 1, so the domain is omega 1, time is between 0 and a. And when time is between A and B, so you get this disappear and this remains. So beta 2 is between 0 and 1. So diffusion, fractional diffusion. So this is a combination of a fractional wave and fractional diffusion equation. So in the rectangular domain, we consider this kind of forward problem. And this is a definition of a regular solution. So here, since we are considering mixed equations, so you need to impose the transmitting conditions. Here's one transmitting condition, another transmitting conditions lies in this regularity condition. So function itself should be considered, should be glued continuously. So we are using the Fourier methods to find the solution. So we have this kind of infinite series. and T1k, T2k are unknowns to be found. And regarding these unknown functions, we got these fractional differential equations involving the regularized Prabhakar derivative. So we know the solution already, and this solution is represented by E2 function. So now when we come back to the solution form, so you need to, when you would like to prove the uniform convergence of infinite series, you need to estimate these functions, and therefore you need to have an estimation of these bivariate Mittag-Leffler functions, and also some differentiation formulas to use to differentiate these functions, and some integral formulas. So some certain properties will be needed. The next application is linked with the Gursa problem for the fractional generalization of hyperbolic type equation. So this is a generalization of a hyperbolic type equation. So here is the regularized Prabhakar derivative is applied on variable y, and also you need to take a derivative with respect to x. And this is just another notation of the Prabhakar fractional integral and the regularized Prabhakar derivative. So here the fractional power, the order is between 0 and 1. So in particular case, you will get this kind of hyperbolic equation. So we impose the Gursa problem for this generalized hyperbolic equation in this form. So we gave a definition of a regular solution. And then we have the following statement regarding the existence and uniqueness of the solution, and also we found in explicit form the solution of this problem. And as you see here, another bivariate Mittag-Leffler-type function will appear, and we number it as E12. So we just continued that, introduced bivariate Mittag-Leffler-type function. So E12 will appear as a solution of this problem. And this is also the stability statement. And also here, you need to have an estimation of this function. This is a new bivariate Mittag-Leffler type function, and it doesn't coincide with the introduced one. That's why we have to introduce and study certain properties of these functions. So regions of convergence is easy, and it can follow from the general result of Srivastava and co-authors. So here we need also some differentiation formulas of this function when we prove the result, and also some integration. This is the Prabhakar integral of this function. Also, we need to simplify. And also, as you see here, we found the integral representation and also the estimate for this function. And these results are used in proving this unique solvability of the Gursa problem. So now, just continuing our research, we considered more general hyperbolic equation. So with the small terms, and with the right-hand side. And as a particular case, you will get this kind of classical hyperbolic equation with the small terms. And for this function, we also, again, considered the Gursa problem. And then solution, we found the solution in explicit form, but it contains the trivariate Mittag-Leffler function. And unfortunately, this doesn't coincide with the existing trivariate function, which was introduced by Arran Fernandez and then later on Anwar Hassanov. But that's why we just have to consider, introduce, and study the new trivariate Mittag-Leffler function. And then, since it was related with the Lauricella hypergeometric functions, we just started to numerate it, just continued with the numeration of Professor Hassanov. So we just F bar E. This was just the fifth trivariate Mittag-Leffler type function. So the explicit form of the solution contains this trivariate function, and this is the series form of this function and the regions of convergence. And also we found the integral representation of this function, here the right functions, and this is a 6-parameter Mittag-Leffler type function. These functions are studied well in some sense. So we got, using these properties of such functions, we found the estimation for this trivariate Mittag-Leffler function, which was used in consideration the Gursa problem. Okay, then we studied the inverse problem. So in our equation 45, the right-hand side depends only from time. And then we are interested to find the pair of functions, the u and right-hand side as well. So this is kind of usual inverse source problem. And here overdetermination conditions will be posed in this form. So here 52 is an overdetermination condition which allows us to find f of t as well. So we equivalently reduce the problem to the integral equation regarding the ft, but also that we found the explicit form of the u as well. So here, regarding with respect to f of t, we got the second kind Volterra integral equation, and the kernel has this, so 2-parameter Mittag-Leffler function and the E2. And the right-hand side contains the Riemann-Liouville derivative of v of t, where v of t also is written in terms of E2, yeah? And therefore, in order to find the f of t, we need to satisfy, based on the general theory of integral equations, we need to show the estimation of this kernel and the continuity of the right-hand side as well. For this, we need to use the estimation of E2s as well. And also here the function was found by trivariate Mittag-Leffler and the E2 as well. And this is, you see that here F3 still appears, and we need to note some remarks regarding the relation of this trivariate Mittag-Leffler function with the E2. So this is a particular case of Fe, so the parameters should satisfy this condition when y is equal to 0. So we got this kind of relation. Also, we can choose another condition on parameters, and we also get another relation with E2. So this trivariate Mittag-Leffler function, when one variable is 0 as a particular case, we can get the E2. That is why in the solution you can see in sometimes E2, sometimes F3E. And when we started to consider another kind of inverse problems or the non-local problems, we faced with the problem of the lower bound for E2. And we started in general case to find the estimate, but it seems very difficult because when you find the integral representation, you need to get the certain properties of the, let's say, the right type function in general case, but the right type function has no this lower bound for certain case, and we consider this particular case, exactly this particular case appears in the solution, and from the previous integral representation for the particular case we got this. But actually you need to pay attention that here this alpha parameter should be equal to 1, and also here we got the for delta greater than 1, it is kind of normal. It's not so restriction to the fractional order, but here we have a delta minus beta greater than 2. It's a bit a stronger restriction on the power. So delta also contains the combination of beta with some constants. So that is why this difference should be greater than 2. Otherwise, we cannot get the lower bound. So with these certain restrictions, we got this kind of double estimate. So I will just would like to show the some proofs. So here from the left and from the right, just the difference is in the constant. So C1 from the left, you got this constant. From the right, you get this. And these integrals, the behavior of these integrals is also studied. So we can get some asymptotic behavior regarding the argument as well here. And the proof is easy. So we just rewrite the series form of E2 and we multiply and divide by this gamma function in order to get the beta function, And we will use the integral representation of beta function. So here, in order to get the positiveness of this power, we have to impose the condition on alpha. Alpha should be equal to 1, so n disappears, and then this can be obtained just in natural way, that delta is greater than beta. So here, just we use the integral representation of beta function, and we got this separate two series in M and N, and this series, this is the two-parameter Mittag-Leffler, and this is an exponential function. And based on the result by Simon and co-authors, this statement is given in a proposition 4. And also here, you see that the beta should be between 0 and 1. And in this case, we have a double estimate, and based on this double estimate, we got the required double estimate for E2. And this estimate was used in the following non-local problem. So the same equation, but in time we use this kind of non-local condition, and we equivalently reduce this problem to the following integral equation with respect to trace of the solution in t equal to 0. And here A has this form where it contains E2. And also the M1 has this form which contains trivariate Mittag-Leffler-type function. So we need to prove, and the right-hand side also contains an explicit form the trivariate Mittag-Leffler-type functions. So here, in order to use the general theory of integral equations, we need to find the bound for the kernel, which is represented by F3E. So this we have this estimation, and we can estimate M1, and also the continuous differentiability of the right-hand side, where we have this function, and also we need some differentiation formulas for this. And E is not equal to 0. It's just comes just to reduce this integral equation to the standard form. And yes, and I would like to note regarding the multi-term. So as you see here, if we consider two Prabhakar fractional derivatives in equation, the trivariate Mittag-Leffler function appears. And there is an ongoing research with another student. We started to consider Euler-type equation, and there 3 Prabhakar derivatives appear, and in the solution, the Mittag-Leffler-type function of 4 variables appear. And as I mentioned, the work by Arran and Fernandez, they considered multi-term fractional derivatives with the regularized Prabhakar derivative, and the solution of this Cauchy problem was found using by Mikuchinsky operational method, and they represent solution as an infinite series of Gorenflow-Luchko function. So I'm expecting that even this trivariate Mittag-Leffler function can be written as an infinite series of a bivariate case of Gorenflow-Luchko function. If we can find this kind of connection, so then the multi-term case of the solution, which was written with the infinite series of this Gorenflow-Luchko function, can be studied in more details. And also I'm very interested in further generalization of such a multivariate Mittag-Leffler function in a sense of Leroy-type generalization. And in this survey paper, Kiryakova, they mentioned why this Leroy-type generalization is important. There are already the very serious reasons to consider such a generalization because they appear in the applied problems. And I'm expecting to have this kind of generalization regarding this multivariate function as well. As I know, it's already started by some professors. I know there's some works Bin Saad and his students, they started also to consider this kind of some generalization of some bivariate Mittag-Leffler-type function. And I hope soon this kind of results will start to appear. And as you see, we have some reasons to consider this kind of multivariate Mittag-Leffler-type function because they appear in the solution of PDEs involved such a Prabhakar fractional derivatives. And I hope this kind of functions will have some other applications in the general theory of special functions as well. So these results presented in this talk were obtained in cooperation with Professor Anwar Hassanov and Professor Niyaz Tokmagambetov and the PhD Dr. Daniel Osmanov and my PhD students Khurshid Turdiv and Muzaffar Tashpolatov. So thank you very much for your attention. I have finished my talk.
Thank you very much. Do we have any questions from the audience?
Well, Arran, can I ask one question, please?
Yes, of course.
Erkinjon, can you open page, for example, 34?
Yes. 34.
Yes. You see, it is a really very interesting talk today we had. And thank you, first of all, for this talk. And also, you see, you have presented many estimates for this many special functions, for example, 23. And here, what is it x and y? Is it small or is it large numbers here?
Actually, in the solution in X, we have a lambda k, which can go to infinity. And y is just it depends on t as well, but with some constant, and it cannot go to the infinity. But when t goes to infinity, when we consider infinite time, so this also can go to infinity. But definitely the x will go to infinity because this variable contains the lambda k which goes to infinity.
So this estimate is not for all x and y. It's only for when x is bigger than 1 and y is bigger than 1. Is that right? For example, if x goes to 0, so is this estimate is true or not?
No, if x goes to 0, it is not true.
Yeah, that's why you should write here x bigger than 1 and y also, right? I think
Yes.
so. Okay,
Yeah,
thank you very much for your answer.
yeah. Thank you.
Thank you. I also have a few comments. I will take more questions from the audience as well, if anyone else wants to ask. So you mentioned a few papers of mine, but I think once you maybe gave me credit that I don't deserve. So if you go to slide 25, you mentioned the Hilfer-Prabhakar derivatives, and you said that we defined this more general case, but we were not the first ones to do that. I think this existed somewhere before. You are right that in the first paper of 2014, they only had n equals 1, but I think the general n was covered somewhere. I'm not sure where. I can ask Tomovsky maybe. He will probably know the reference.
Yep, might be.
But
It might
it
be
was
the
not
publication
thorough, yeah.
in 2016. Professor Tomovsky and Polito considered in 2016 as well some properties of Hilbert-Prabhakar. So it might be, and introduced it in that paper as well.
Is that Gara and Tomovsky paper?
Yes, it's a fractional differential calculus, Polito and Tomovsky in
Polito,
2016.
Tomovsky, yeah.
Yeah. And there are some papers of Anastasius from USA as well. He has even the book on Prabhakar fractional calculus. And there are some papers on this Hilfer-Prabhakar as well. So I was a bit confused with this ordering the publications. And nowadays it's not easy to follow all the results, especially which was even if it's not published, so it's not easy to follow. And also, I forgot to mention the work by Salman Malik, where they considered inverse problem, but they used this infinite series of this Prabhakar function, and somehow they proved this the non-zeros, just in denominator it appears this infinite series, but somehow they proved, but I didn't study it yet, that paper. Without introducing the special bivariate function, they handled the inverse source problems. They considered 3 types of inverse source problems, and it was also recently published into 2023.
Yeah, I think I've seen that paper as well. On slide 23, just 2 slides back, there is a interesting point here that equation 18, it looks like it is a particular case of the equation above, choosing mu equals m specifically. But actually, it's not really a particular case because any value of mu greater than beta will give, in fact, the same operator. So when you either if you expand it as a series or if you use some semi-group relations of Riemann-Liouville, you can prove that the formula in the first equation does not depend on the choice of mu. Whatever mu you put, it will be the same as equation 18.
Oh, it is just that depending on the introduction of the definition of the Riemann-Liouville. Usually they introduce in the integer case, it is just a normal derivative.
Yeah, but they use this choice of mu equals m because it is the most easy choice, the ceiling of beta. But in fact, it would be the same for any choice of mu. An interesting fact and not obvious, but I thought it's worth mentioning. On slide 10, so between slides 9 and slide 10, you look at 2 different multivariable Mittag-Leffler functions with different types of Pochhammer symbols on the top. I think that these are not special cases of each other, but rather different directions, because in this one...
You mean regarding this series?
Yeah, so this one, equation 7, it could be written as an m-fold sum over delta sub k1 plus ... plus km, whereas the other one has a product of m different Pochhammer symbols on the top. And I think you cannot turn one of them into the other by taking a particular case.
It depends. I tried this Gorenflo-Luchko in a bivariate case, if you see that it is written in this form, so in bivariate case, you can write as a double infinite series. And here, this gamma functions will be a bit different, but you can write with other bivariate functions as well. So I write with the E2, this bivariate case of Gorenflot-Luchko. I wrote with a particular case of E2. So maybe I was a bit confused. So I don't, maybe I didn't read carefully this paper because they considered bivariate case as well. In that case, it might be checked. So will this follow from this? Probably, I don't know. If it follows, though, they should mention. But Professor Bajlekova, in previous talk, she gave enough detailed information about this function.
Yes, so equation 6 is a particular case of equation 7, but equation 7 is not a particular case of equation 8 because the nature of those Pochhammer symbols is going to be different. In the bivariate case, it would be like delta K1 plus K2 or gamma 1 K1 times gamma 2 K2, and those are two separate behaviors coming out of them.
Yep, might be. Thank you. Thank you for mentioning.
One more question. On this slide, you mentioned asymptotics have been studied. Where do you have a reference for where these were studied or who studied asymptotics of these functions?
You mean this or this?
Well, both of them.
This one is kind of you can find in the Yamamoto's and also the Karl van Boxtal's where they consider the estimate. So you can interpret it as asymptotics as well. So they put certain conditions on the arguments and they found an estimate. For the Yamamoto, they found the estimate, and then Karl van Boxtal, they just improved the conditions on this function. But regarding this function, more information was given by Bajlekova in previous talk, and they studied the complete monotonicity, which is also important, and we are expecting this kind of results on this bivariate and new trivariate Mittag-Leffler functions. It will help us to in detail to study the behavior of such problems. The Professor Ashurov knows about more because they also apply this complete monotonicity and other properties of even this classical Mittag-Leffler function, and they get new results. So this kind of properties will be indeed used in future if we got this.
Okay, thank you. I will check and search for those papers. Thanks.
Thank you for your questions.
Do we have any other questions or comments? You can unmute yourself and ask, or you can type in the chat. If not, then once again, we thank our speaker very much. It was an interesting presentation, and I will close the session for today.